Okay, so welcome everybody to today's edition of the Pacific Quasiworld seminar. Our first speaker is Hao Wu, and she will talk about connection probabilities for loop ON models and BZ equations. So please.
Okay, thank you for the invitation. So it's my great honor to be speaking at this quasi-Pacific seminar. So my topic may be a little bit far from quasi-conformal. So basically, it is conformal. Okay, so my talk will have two parts. The first part is about the loop ON model, and the second part is a special case for the loop ON model. So it is called the uniform spanning tree. So the definition for the loop ON model is pretty simple. So let us focus on the model on the hexagonal lattice. On this graph, so we sample loop configuration, so meaning that we sample some edges to be open and some edges to be closed. And the requirement is that we only allow loop configuration. So all the edges has to form a loop configurations. So this is why this is called a loop ON model. For this model, there are two parameters. One parameter is n, and another parameter is p. So for each loop configuration omega, the probability for this configuration is given by n to the number of L omega. So this is the number of the loops times p to O omega. So this is the number of the open edges. So this model has two parameters. And then the first question is whether this model has critical physics. So the answer is like this. So suppose we fix n in the interval between 0 and 2, then there exists a critical value Pc, so that when P is less than Pc, the model is subcritical. By subcritical, we mean that if we calculate point-point correlation function, this correlation function is going to decay exponentially fast. And the interesting part for this model is that there are two critical phases for this model. So the first critical phase is when P equals Pc, and in this phase, physicists conjecture that the system of this model will become conformally invariant in the scaling limit. And there is a parameter corresponding to SLE curve. And in this case, the parameter kappa is between a-thirds and 4. And when P is bigger than Pc, so this model is also critical. So this is very different from the usual model we considered. And the physicist predicts that in this critical phase, the scaling limit of the model will also become conformally invariant as the scaling limit. And here, there also corresponds to a parameter SLE kappa for kappa hat. I denoted by kappa hat. And this kappa hat is between 4 and 8. So, and in the left-hand side, we see a phase diagram of this model, and this model combines many famous models that we have heard. So, for instance, the horizontal line is the n parameter, and the vertical line is the p parameter. And here, this blue curve here is the graph for this PC. And in this model, in the ON loop model, we see that our favorite Ising model is here. So it corresponds to n equals 1 and n equals 1 and p equals 1 over square root of 3 here. And in this model, we also have our famous model called the self-avoiding walk. So this model corresponds to n equals 0 and then p equals 1 over square root of 2 plus square root of 2. So this number is the famous connective constant for the self-avoiding walk. And here we'll have our model when n equals 1 and p equals 1. This is the famous percolation model. And here, when n equals square root of 2, p equals 1, this is the famous FK-Ising model. So this is the model that is dual to the Ising model. And the last model in this picture is called the uniform spanning tree. So here it corresponds to n equals 0 and p equals 1. So this is the 5 special models inside this loop ON model. So according to the conjecture, all the model on this critical line will become conformally invariant, and all the model above this critical line will also become conformally invariant. For this conjecture, for these four models that we already know that the conjecture is proved to be true, so they are the uniform spanning tree, percolation, FK-Ising, and Ising. And for self-avoiding work, and this is still a open conjecture that it is conformally invariant in the end. Okay, so this is the background for the loop-O model. And in my talk, I will be interested in what is the connection probability for the loop-O model in a polygon. So now I will introduce what is a polygon and what is the connection probability. So in this picture, we see that this is a polygon of six marked boundary points. And in this graph, we fix 6 boundary points. So this is a polygon with 6 marked boundary points, and we'll fix a boundary condition. The boundary condition is that we require all the edges from 1 to 2 to be contained in the configuration, and all the edges from 3 to 4 have to be contained in the configuration, and all the edges between 5 to 6 has to be contained in the loop configuration. Fix this boundary condition, and then we sample this loop-O model according to the probability measure. After we sample complete all the loop configuration, then we see that these 6 marked points will be connected pairwise by the loop configuration in this loop-O model. So for instance, in the first picture, 1 is connected to 2, 3 is connected to 4, and 5 is connected to 6. So the loop configuration will give a planar link pattern between the 6 marked points. And in the second picture, we see that 1 is connected to 6, 2 is connected to 3, and 4 is connected to 5. So this is another different link pattern. And then my question is, can you calculate what is the probability for each link pattern in this loop-O model? And then conjecture is the following. If we fix the parameter n between 0 and 2, and we fix corresponding parameter kappa between A0 and 8, and then we are able to calculate what is the probability for each link pattern in this model. And the conjecture says that if we fix a boundary condition beta, and then for each internal link pattern alpha, the probability for alpha to appear will have a scaling limit. And the scaling limit will be given by these 3 quantities. The first quantity, m, is what we call meander matrix. And the f here, this is a function in the location of the polygon of the 2 unmarked points. And this is what we call Coulomb gas integral. And this z alpha, it is also a function in the location of the 2 unmarked points. This is what we call pure partition functions. And I will introduce these 3 quantities one by one. For the meander matrix, so this is a matrix. The size of the matrix is a Catalan number by Catalan number. At each entry, alpha and beta, so the number of the matrix at this entry is given by this formula. So first, we draw our link pattern alpha in the upper half plane, and then we draw the link pattern beta also on the upper half plane, and we take the horizontal reflection of beta to the lower half plane, and then we merge alpha and beta in order to form a loop pattern, and this pattern is called meander between alpha and beta. And in this meander, we count the number of the loops in the meander. And then the matrix at the entry alpha beta is given by n to the power of the number of the loops. So this is meander matrix. For this matrix, it has been very well studied. And in my talk, I'm interested when this matrix is invertible or not. And the conclusion is given by Di Francesco, Goninelli, and Gitter in 1997. So the conclusion is that the Meander matrix is invertible if and only if this parameter kappa has to be between 0 and 8 and remove certain rational numbers. So this is an if and only if condition, so we know very well whether this matrix is invertible or not.
Can I ask you a quick question just to make sure that I understand what is going on? In your case, right, I mean, just for these hexagons, this is a kind of small matrix, right? Because there are not too many configurations, right? Or
yeah, so in this example, when there are 6 marked points, the Catalan number is 5, and this is a 5 by 5 matrix.
Okay, all right.
And when the number of the boundary points is more, so the matrix can be very large. Okay, so this is the first quantity Meander matrix. The second quantity we call Coulomb gas integral. So this function, so is by definition is an integral, and the integrand function looks like that. So this is basically a polynomial. So we have 2 unmarked points on the real line. So they represent the location of the 2 endpoints of the polygon. And this is this integrand function is a polynomial. So there are n integrand variables from u1 to un. And the integrand function is a polynomial. And the integration surface here will depend on the link pattern beta. So for each link pattern beta, so we pair these 2 endpoints according to this link pattern. And the integration surface is the integration surface that we draw the Pohammer contour around a pair in this link. So there are n-fold of the integration surface, and this is the integrand function. And here we see that although the integrand function is pretty simple, but it is a multi-valued polynomial function. So in order to make the precise definition, we need to specify what is the branch of this integrand we are chosen. So here, the branch of the multi-valued integrand is chosen to be real and positive in this range. So the idea why we want to do that is that, in fact, eventually we hope this integral function is positive, because finally it will appear in this conjecture as part of the probability. So in order to be as part of the probability, it has to be positive. So we choose this branch with the purpose that we hope this function to be positive after we took the integration. Okay, so why we are interested in this kind of Coulomb gas integral? Because physicists find using the representation theory of the Virasoro algebra, they find that if we want to understand the solution to this second order BPZ equation, and you plug in this ansatz in this way, and we find that the definition of this form will always satisfy the BPZ equation. And the proof, in fact, is pretty simple. If you just naively switch the differential operator and the integration surface, then you can immediately check that this polynomial will satisfy this second order equation. So therefore, this function will satisfy the second order BPZ equation. Okay, so then let us come back to a few properties of this Coulomb gas integral. So first, when we choose this integrand branch, we already say that we hope this function is positive after we do the integration. And then the question is whether it is indeed positive or not. And the answer is that whether it is positive or not depends on the parameter. So when the kappa is between A-thirds and 8, this integral is indeed positive. And when kappa adds these 2 terminal values, A-thirds and 8, this function is 0. More than that, we also know how fast it goes to 0. So as kappa goes to 8 A-thirds, so this function will converge as a power in kappa minus A-thirds to the power 1. So after we normalize this decaying rate, we get a positive limit. And when kappa goes to 8, we normalize this 8 minus kappa to the power n, and we also get a positive limit. So we not only know that they are 0 at those 2 terminal values, we also know how fast it decays to 0 as kappa approaching those values. And when kappa is less than A-thirds, in fact, those functions can be negative. So there are 0 points, and there's a detailed analysis of this function.
Can I ask a quick question again? So can you say something, how does one prove such things? Can you say one or 2 sentences about this?
Yeah, so in fact, what we do is we first explicitly calculate the integral when there are only 4 marked points on the boundary. And here we can already see all the phases. So like they are positive in this interval and they are 0 here, and they can have zero points there. And in fact, for more points, it is pretty complicated to read this information from this formula. So in fact, I will show how we prove in 2 pages. So in fact, we prove it through another collection of the solution to the BPZ equations. Okay. Okay, so the second collection of the functions appeared in this formula is called the pure partition function. So for this pure partition function, by definition, we define it in this way. So they are solution to the BPZ equations. So this is exactly the same system of the BPZ equation as in the previous page. More than that, we also require that this collection of functions satisfy a certain boundary value problem. So the boundary value is like this. Suppose this is our polygon, and suppose we have 2 neighboring points, xj and xj plus 1. And when these 2 points are very close to each other, we require this function has to explode in a certain way. And after we normalize by this explosion, we give a specific limit when the 2 points are shrinking together. So this is a very special choice of the boundary value to this BPZ equation system. So now I will explain a few words why we choose this boundary value. So recall that our idea is to calculate the probability for the link pattern in this polygon. So now suppose these 2 points are very close to each other, we can imagine that the probability for this picture will converge to the probability to this picture. So therefore, if we calculate this system of the probabilities in the polygon, so this probability will have certain compatibility, by meaning that when these 2 points are very close to each other, the probability in this pattern for the n curve will converge to the probability for this pattern when they are a -1 curve. So this system of the probability will have certain compatibility. And this boundary value is chosen in the way that we want to make this compatibility possible in this definition of the functions. So this is the reason why we choose this boundary value. And now after we give this definition, the most natural question is whether there exists such collection of the solutions satisfying the BPZ equation and the very specified chosen boundary value. And the conclusion is yes, this collection of the pure partition functions, they exist and is unique for all kappa between 0 and 8. Okay, so for the proof of the existence and the uniqueness has a pretty long history. The first proof comes with the uniqueness. So Floch and Coulomb proved in 2015 that once this collection of functions exists, they're going to be unique. And for the existence, there are at least 5 articles construct the solutions for different range of the kappa between 0 and 8. And now overall, we can say that we have the existence for all kappa between 0 and 8. So the quick information is that although this definition looked pretty strict, but we do know that there exists a unique collection of solution to this boundary value BPZ equation system. And for this collection of the solutions, in fact, we have more information. They are linearly independent and they form a basis for the solution space. Moreover, for this collection of pure partition functions, they are always positive. And when kappa goes to 8, this collection of function will tend to 0. And we also know that how fast it's going to converge to 0. So it's at a polynomial rate in kappa. And here I also want to mention another conclusion in this story, but not so by my good friend. So Evelina Peltola and Yilin Wang also proved that when kappa goes to 0, in fact, this collection of pure partition function will decay exponentially fast. So here we have a pretty complete picture. So at when kappa between 0 and 8, they are always positive. When they approaches 8, they become 0 at a polynomial rate. And then when kappa approaches 0, they decay to 0 at an exponential rate. Okay, so this is the introduction. This is the property for the pure partition function. Now, let me come back to your question, how we prove that the Coulomb gas is positive or not. So here I introduced the two collections of the functions. One is called the Coulomb gas integral, and another collection of functions called the pure partition functions. Both of these functions, they are all solutions to this second order BPZ equation. And I also mentioned that these pure partition functions, they form a basis for the solution space. And as the Coulomb gas integral is also a solution, then the Coulomb gas integral can be written as a linear combination of the bases. And this is the case. So the Coulomb gas integral can be written as a linear combination of the bases. And this linear coefficient is given exactly by this Meander matrix. And here I can now come back to your question. So here, because the Meander matrix N is in this way, so it can be negative. So we already know that all these pure partition functions, they are positive. And if this Meander matrix is also positive, then of course the Coulomb gas will gonna be positive. But the Meander matrix, this coefficient can be negative. And then when it is negative, this is the case that the Coulomb gas can also be negative. So this is how we prove that this big integral formula is positive in certain range. So we do not prove it directly by analyzing the integral. So in fact, we prove it by this linear combination relation. Okay, so this is the introduction to this three objects in this conjecture. So we already know that this is Meander matrix, this is Coulomb gas integral, and this is pure partition function. And from the linear combination relation, we also know that for the right-hand side, if we summing over all possible alpha, this is sum up to 1. So this is exactly the linear combination we have seen in the previous page. And this also makes this conjecture more reasonable. So this right-hand side is a probability, and if you summing over all possible cases alpha, then it sum up to 1. Okay, so this is the three quantities in this conjecture. And now let us come back to the conclusion. So now for this conjecture, what is known? So which cases is proved? So we already recall that for this loop or model, the physicists conjecture that they are conformally invariant in the end. And there are 4 models that we can already be able to prove that they are indeed conformally invariant in the end. So they are Ising model, FK-Ising percolation, and the uniform spanning tree. So this 4 model, we already know that the model is conformally invariant in the scaling limit. And for all these 4 models, we can also prove this conjecture that the connection probability is given by this formula in the right-hand side. So they are the uniform spanning tree, percolation, FK-Ising, and the Ising model. And here I also want to mention 2 explicit formula for the Coulomb gas integral. So when kappa equals 6, we can check that this Coulomb gas integral is identically 1. So although it is still defined as an integration function of a complicated polynomial, but we can show that in fact it is identically 1. And in particular, it has nothing to do with the boundary condition. And this is consistent with what we know from the percolation model, because for the percolation model, the edges are independent from each other. So the model has nothing to do with the boundary condition. So this is also consistent. And another case for this Coulomb gas integral is when kappa equals 3. When kappa equals 3, this Coulomb gas integral also have a very explicit definite formula. So this is the Pfaffian of the function in the at each entry. It is xj minus x1 over 1 over xj minus xi. So this formula is also very concrete, and in fact, this formula is predict from the Ising model, the energy field of the Ising model, and in this formula, we also see that this formula has nothing to do with the boundary condition. So in fact, these two formulas are very special here. In fact, both of them corresponds to the fugacity equals 1. So that's why they have nothing to do with the boundary condition. And this relation also is a special case in the loop ON model, that there's another conjecture for the loop ON model, that we have another duality between parameter kappa and the kappa hat. So they corresponds to the dilute critical phase and the dense critical phase. So when kappa and the kappa hat are related by this formula, they correspond to the same model. One is the critical phase, and another one is the P bigger than PC, so a different critical phase. And in this conjecture, in particular, percolation and the Ising model, they are conjectured to be due to each other by this formula. So 1/6 plus 1/3 is 1/2. Okay, so this is the conjecture for the connection probability for the loop ON model. And now I go to the second part of the talk. So I will focus on what happens on the on the uniform spanning tree model. Here we're gonna see something more interesting related to the conformal field theory. Okay, so let me first briefly recall what is the uniform spanning tree. So of course you can view it as a loop ON model when n equals 0, but of course we can also define it directly. For a uniform spanning tree on a graph, so we start with a finite graph. A tree is a subgraph of tree without loops. A spanning tree then is a tree that covers all vertices. So if the graph is finite, then the number of such spanning tree is finite, and the uniform spanning tree is the probability measure that we choose a spanning tree uniformly among all the possible spanning trees. And now we consider the uniform spanning tree in a polygon. So here in the left picture, this is a polygon with two marked points A and B. And in this polygon, we require that all the edges from A to B is contained in the configuration. And after we put this specific boundary condition, and then we sample the uniform spanning tree according to the probability measure. After we draw the tree, then in fact we can draw this orange curve. So this orange curve is a curve live beneath the tree and the dual tree. So this is a piano curve. And the very famous conclusion in this direction is that in around 2000, Lawler, Sherman, and Werner prove that this piano curve is conformally invariant in the scaling limit, and it converge to SLE8. Okay, so this is the uniform spanning tree in a polygon when there are two marked points on the boundary. And now we can consider this model in a more complicated polygon. In the right picture, so this is a polygon with a 6 marked point. And our boundary condition is alternating. It means that all the edges from 1 to 2 is required to be contained in the configuration. All the edges between 3 to 4 is contained in the configuration. And all the edges between 5 to 6 is contained in the configuration. After we fix this boundary condition, we just sample the uniform spanning tree according to the probability measure. And then we see that we draw the piano curve between the tree and the dual tree. And then this probability pattern, the measure, the configuration, will result in a link pattern between the 6 points. So the piano curve will form a link pattern between the 6 marked points. Here is an example when consider the uniform spanning tree in a polygon of 8 marked points. And for this, in this model, in fact, this wired arc along the boundary, they can be further connected in a planar way from the outside of the polygon. So this is the boundary condition for the uniform spanning tree. And then for the inside of the polygon, I just sample my uniform spanning tree, and these boundary arcs will be connected by the uniform spanning tree in the inside. And now I want to encode what is the meaning, how to encode these planar link patterns. And the encoding is like that. So first, I draw outside of the polygon the link between the marked points so that they never cross the tree and the dual tree. So now this boundary condition has a one-to-one correspondence between the link pattern of the blue curves here, between the link pattern among the 8 points outside of the polygon. For the inside, I follow the same rule. I also draw the curves between these 8 points so that they never cross tree and the dual tree. And this is going to result in the blue curves in the inside of the polygon. So this red curve also give a planar link pattern between the two unmarked points. Okay, and in this particular example, we see that we can encode the boundary condition by a planar link pattern beta. We can also encode the internal link pattern. So here there are 4 cases by a planar link pattern. And then the question is, for each given boundary condition and each internal link pattern, what is probability for each pattern to appear in this model? And here we also recall that in this model, we are interested in this renormalized meander matrix. So recall that our usual meander matrix is defined in this way. So it is n to the power of the number of loops in the meander. So in the uniform spanning tree model, n equals 0. So therefore, this meander tree matrix is identically 0. But in this case, we can still normalize this matrix so that it is not 0 everywhere. And this normalization is called a renormalized meander matrix. It means that at each entry, I normalize this value by 1 over n. And then it's going to converge to the renormalized meander matrix. And the definition of the renormalized meander matrix is also simple. So it only remembers which meander has only one loop, and then it has an indicator function 1 here. Otherwise, it is 0. So here we see that this renormalized meander matrix, in fact, it is very sparse. So it only have a few ones, and most of the places are 0. But the funny thing for this renormalized meander matrix is that although it is very sparse, but it is still invertible. Okay, and then our previous conjecture for the loop over model will become this formula in the uniform spanning tree. So now we want to ask, what is the probability for each pair of alpha beta? So beta is the boundary condition. Alpha is the internal link pattern. So what is the scaling limit of the probability for the uniform spanning tree? And the conclusion is that this probability is again given by these 3 quantities. Here is the renormalized meander matrix. Here is the renormalized pure partition function. And here is the renormalized Coulomb gas integral. So before we set kappa goes to 8, in fact, those 3 quantities are finite and they are well defined. And all of the 3 quantities will converge to 0 when kappa goes to 0. But we know how fast it's going to converge to 0. So we normalize them properly so that then we still have a non-zero limit. So this is the formula. This is how we get to this formula in the right-hand side. So this is here is the renormalized meander matrix. And this is the renormalized Coulomb gas, and this is the renormalized pure partition function. And the interesting part is that although this matrix is very sparse, but it is still invertible. Okay, so now let me briefly recall how we prove this kind of formula. So in fact, in all the 4 proofs that we derive this connection probability formula, they all have the three steps. The first step is that we need to identify the limit of certain allomorphic observable. So here in the first step, we need to figure out what a proper allomorphic observable on the discrete and then identify the limit of such allomorphic observable. Once we have such observable, in fact, the second and the third step are pretty standard. The second step is that we try to solve the Loevner equation driving function from this allomorphic observable. This will make appear the partition function of the Coulomb gas integral here. And then we have a very refined analysis on the martingale, which is given by the ratio between pure partition function and the Coulomb gas. So this martingale has, it is pretty complicated, but once we know the properties of those two collection of the functions, we have ways to control those martingale, and then and then we apply the optional stopping theorem to calculate the probability. So all the three models, we follow exactly the same three steps. Among these three steps, in fact, the first step, the proof for the first step is usually very quick. So it's usually 2 or 3 pages. But in fact, this step is the most difficult one because we need to figure out what is a proper holomorphic observable. Once we know the first step, from the first to the second and from second to the third, the proof is usually very long because it is rather technical. But basically, this is just a technical work. So once we figure out the first step, then the second and the third is just a problem of time, so we can eventually solve them. Okay, so this is the proof, key steps in the proof. Here, I also want to mention a cute formula here. So for the uniform spanning tree model, in fact, we know what is the proper holomorphic observable. In particular, we can identify this holomorphic observable, the limit of the holomorphic observable, and in the limit, in fact, this limit is given by this Christoffel-Schreib's formula. So it is pretty simple. Okay, so now I want to mention something how we see the connection to the conformal field theory. In fact, from the physics paper for the uniform spanning tree, this model is predicted to be related to the CFT, but with logarithmic correction. But in the physics literature, because it is not very well defined the field behind the model, so it's not very clear how to make sense of the connection to this logarithmic conformal field theory. And now in our paper, in fact, we make a concrete connection how we see this logarithmic correction in terms of the partition functions. So in fact, what we do is that for this Coulomb gas integral, we take the Frobenius expansion of this of those functions. So when x1 and x2 are very close to each other, the leading order of the decaying is a polynomial. And the second order is a small term. This in the case that when these 2 points are paired together, but if the 2 points are not paired together, in fact, the leading term is a polynomial with a logarithmic correction. So here we make first a concrete connection to this logarithmic correction in the conformal field theory. So this partition function, they can be viewed as there's a certain relation to the correlation function in the conformal field theory. And for those Coulomb gas integral, this partition function, we do see that there's a logarithmic correction here. And here we also compare it with the prediction from the physics paper about the operator product expansion of the conformal field behind the uniform spanning tree. And here, this asymptotic is consistent with what we have in the Coulomb gas integral. And here our future work is that, so here is just the first hint that there is indeed a connection to the logarithmic conformal field theory, but still we don't know what is the precise connection. So the future work is that we're gonna continue this direction and see how we build up the precise connection between the probability model and the conformal field theory, and how to figure out what are the our holomorphic observable in terms of the conformal field theory. And also, by the way, for the uniform spanning tree, the predict conformal field theory behind the model corresponds to the central charge C equals -2. Okay, so this is the end of my talk. And here are some references that is related to me through the talk.
Okay, thanks a lot. Let's thank our speaker. And let me open the discussion, comments or questions. Now, let me ask you another question. So you mentioned in this work by Lawler, Schramm, and Werner, right? I mean, they showed
yes
that, the limit, right, converges to SLE8.
Yes.
Can you say something similar in your models?
Yes. So in fact, when there are only 2 marked points, the limit is this SLE8. And when there are more marked points for the general polygon, we also identify the limit. The limit is the Loebner chain. associated to this Coulomb gas integral. And in particular, when there are only 2 points, this is exactly SLE8. But when there are more points, it is just more complicated. So it's a it is a variant of SLE8 process.
So there are several kind of arms growing at the same time, or how should I think about this in this more general model?
So this more general model. So if you only look at one curve,
yeah.
So this is basically absolutely continuous with respect to SLE8, but the random Nicodim derivative is given by this Coulomb gas integral.
Oh, I see.
Yeah.
Okay. All right.
Yeah. So it is a variant of SLE8. It is SLE8 weighted by this Coulomb gas integral.
Okay. Are there other comments or questions? Well, doesn't seem to be the case. So let's thank Hao again.
Okay, thank you.